Imagine a world of waves. In physics, waves are defined as disturbances that propagate through a medium. For instance, sound waves travel through solid, liquid, and air. When we express the speed of sound in dry air at 0 degrees Celsius as 331.3 meters per second, we are considering an observer and a corresponding reference system fixed in the air mass through which the sound wave is traveling. This air mass functions as the medium for the sound wave. Therefore, waves exist everywhere and they travel through different mediums. But what about light? Through what medium does it travel? Is it air? Let's call this ambiguous material ether. Ether is an invisible nothingness that permeates the universe. If an ether truly exists, the spinning and rotating Earth should be moving through it. An observer on the Earth would sense an ether wind whose velocity is relative to the Earth if we were to assume that velocity equals the Earth's orbital speed about the Sun, about 30 kilometers per second. An extraordinary level of precision was essential to measure such a small difference. It was Albert A. Michelson who devised the Michelson interferometer. The Michelson interferometer is an apparatus that splits a beam of light into two perpendicular paths, reflects the beam, and then recombines them to create an interference pattern. Here's how it works. A beam of light originates from the source. This partially silvered mirror is placed at a 45-degree angle. It splits the incoming light beam into two perpendicular beams. One beam reflects off the beam splitter at a 90-degree angle and travels to mirror 1. The other beam passes straight to the beam splitter to mirror 2. Both beams travel equal distances to their respective mirrors, reflect toward the beam splitter, and recombine. When two light beams merge, their synchronized waves either amplify each other's peaks significantly, or if they are out of sync by half a wavelength, their peaks can cancel each other out. Minor variations in the speed of these light waves result in an interference pattern. No shift in the interference pattern was observed. The results were consistent regardless of the apparatus's orientation. The null result puzzled the scientific community until 1905, when inspired by the Michelson-Morley findings, Einstein proposed the special theory of relativity. He posited two revolutionary ideas. The laws of physics are identical for all observers in uniform motion, and the speed of light in a vacuum is constant regardless of the motion of the source or observer.